Okay, this is a demo for MOSFET simulation. In most of the MOSFET simulation in the textbook, we have to use 4-pin MOSFET because the 3-pin MOSFET has already been reduced to a simpler model, so you cannot use like length of the channel and width of the channel as the design parameters. So let's start with MOS4. Okay, for the MOS4 it has 4 pins. For example, I'm going to do a differential stage in the textbook, so I put 2 here, M1, M2. So these are the 2 MOS, and then I would like to put the ground here, and also with the current source. So the current source is this. So it's here. Okay. So that's the design problem. So let's redo it again so we can adjust a little bit so to make the figure to be more schematic, to be more compatible in this circuit. So here I get these 2 connected, and here connected, and here connected, and both of these are connected here, right? And there's a load resistor here, and how about the power supply for the differential stage? You just take a voltage source here and put it aside and put a ground, and again you put a connection wire here. So okay, and then I put a connection port or label here. Label is like, for example, I put to input, and I call it VDD, and then just one put it here and the other one put it here. Okay, and that's VDD here, and we want to put a V in and a VB. So there are 2 extra voltage sources here. One is one here and one here. So we still put the 2 sources here, and then we connect this together. Okay, for most of the MOS, the body is connected to the source, right? So it has to be connected like this. Alright, so now we can change the signal. Here is the V in, and this is a bias source, we call it VB. Okay, and of course there's the output port. So I'll get an output port here, I call it out, V out, and it's output port. Okay, that completes the circuit, right? But we haven't defined all the details, so now I would like to save it just in case I erase it. So the problem is like 7 6. Okay, now it's saved. So let's now define the circuit. The VDD is 1 point. Okay, so we assume VB is 1.2 and a cascade. So Here we assume it's 1.8 volt. It's 1.8, and here the V in 1.2 and VB is 1.2. And the bias current is 1 milliamp. And the R is 1 kilo ohm. Now we want to define this NMOS circuit, right? So we use the model directives, okay? So the model directive is dot MODL model NMOS. Here the NMOS will be defined with this. This NMOS is really a NMOS, and the KP is 200 mu, as in the beginning of the the problems. So it's 200 microamp, and VT O is 0.4, right? That's what it. Now we define the NMOS, so that's 0.4. And lambda, of course, lambda is 0, so it's default. I don't have to model it. Now, since we have complete model, we want to determine the voltage gain, right? It's easy to simulate, okay? And what we haven't defined is the two MOSFET width length geometric parameters. Okay, they are both 10 micron to 0.8. So here I right click, here the dense, and length is 0.18, and the width, they are both 10 micron. Okay, if I want to get the parameter out, control, right click, and then I can show it, and control right click, I can show it. So I haven't defined this. This is 0.8, 0.18, and this is 10 micron. Again, plot it out. Okay, both two of the parameters are here. Okay, that's the differential stage. Let's look at how do I know what's the voltage gain. Okay, so Vin is here. So we'll change Vin into a AC source. Advance, it's a sine. The bias 1.2, and we'll put a small voltage, 10 millivolt here, and with 1 kilohertz. Okay, and now we can do the sinusoidal simulation. So we do the transient with 10 milliseconds for 10 cycles, and minute time step I use 10 micron. Now I can do the simulations. Let's run it and look at the output. Okay, that's the V out. Okay, here you see that's here, and of course we have to know what's really the bias condition. So it's from 1.24 to 1.3, so we can actually try to view the average. Let's calculate the average. So let's first do the operational point. So get the DC out. OP point. OP. Sorry. That's the operational point. Then we click it. And it tells you that the V out is at 1.3 volt, right? And VDD is 1.8, so 1.3. So I will take the 1.3 out when I do the AC simulations. Okay. Here we do the AC again. And run it again. And trace V out, and now I can take the 1.3. So now it's the result, right? And I can also use a division of this. So I can use this, the mathematics operation of this divided by V in. V of V in minus 1.2. I should put a label here. V. Okay, now I can do it. I will edit it. Divided by V in minus 1.2. Okay, now the gain is here. Look. It's about 1.5 to 1.8, so you click here, you get the gain is 1.67. So the voltage gain is 1.67, right? That's how you get the voltage gain. That's 1.67. And of course, we can look at the output. We add the propane. We look at output. That's the V out. We can also look at the input. V in. See here? That's what happened here. So the gain is 1.67. Here, 1.67 here. 1.67 here. You can easily get about 1.67. That's how you really do the simulation here. Okay. So you have to know that because I can design the geometric factor here, so the amplifier can really give you the result. Okay. So if I reduce the voltage here for 10%, that's about 1.2, that's 1.02. And then what will happen? So I go here, 0.08. Okay. And then again, if I run the simulation, I take it out. Here I'll do oops, sorry. 1.08. 0.08 V in minus 1.08. and the V out is, sorry, obviously it's wrong. I have to redo the operational point here. The up here, and then get it again. The V out becomes 1.104, 1.104. So go back again. 1.104 and simulate it, and then I'll take the 1.104. Now take 1.104 divided by minus 1.02. VO 1.1 Y VO divided by V in 1.08. Sorry. Now look, the game becomes so small. So I think then the problem do show out here. If I change the BIOS, then the gain is totally gone here. Let's check it again. (1.008) to 1.1989 to 19. That's about 20 millivolt, and here is 10 millivolts. So the gain is almost just, well, it's 1. There's no gain. Okay, you can look at here. So if I minus 1.104, can you see? It's 15 millivolt, and here I have 10 millivolt. So the gain is 1. If you change the BIOS, the gain is 1. Okay? That's really what happened here. Okay.